Good evening, everyone. Am I audible? Say yes or no. Can everyone hear my voice? I think it's clear only. Anyway, if you have any issues, just make a WhatsApp call. Okay, let us start the next part. So anyway, we are designing what counter circuits, right? We saw there are two type of counters. One is called synchronous counter and another one is asynchronous counter, right? So we are designing asynchronous counter. In asynchronous counter, right? So initially we are discussing about up counter and down counter. So basically in the last lecture, right? See, we saw how to design up counter and down counter. I think I took negative edge triggering, right? So let us take positive edge triggering, right? Once again we will take the same type of circuits. Let us see how to design the counters, right? So instead of naming them directly, first we should understand, right? Guys, post your comments in the comment section. I can't see any one of your text. Fine. So let's continue our journey with the next type of counter. So let us design. Once again, let me consider. Wait a minute. It is better to go with these two. Yeah. So let me take next type, right? So once again, we will consider same three counters. That is, take three flip flops, right? So we are going to consider three flip flops, right? We are going to consider three flip flops, right? In these three flip flops, that is, we are going to keep what? T flip flop only, right? So we are going to use standardly T flip flop. I said here we are starting. This is our MSB, right? And we are going to, that is the portion, that is this is the flip flop in which we are giving the clock. This is the LSB for us, right? Anyway, we are going to start our journey from Q0, Q1, and this is going to be Q2. Let me call it as T0, T1, T2. Now, since we are designing what asynchronous counter, so we are designing asynchronous counter. Asynchronous in the sense, only first flip flop will going to be triggered with the help of clock, right? Whereas the second flip flop will going to be triggered with the help of output of the previous flip flop, right? Will going to be triggered with the help of output of the previous flip flop, right? Such that, let us see, in order to design, right? So in order to trigger this flip flop, let me take the output from here. Let me inject it as a positive edge triggering. Again, let me take the output of this flip flop. Let me connect it. Let me treat this one as a clock, and I will trigger the next flip flop with the help of this one. Such that we all know, in order to design the counter circuit, the most important part is we can consider either JK flip flop or T flip flop with the input as 1. That is the most important condition, right? And then we are traveling along with the two type of edge triggering. Either it might be positive edge triggering or negative edge triggering, right? Already we saw how to design the asynchronous counter with the what? Negative edge triggering, right? Now we are going to design the same asynchronous counter with the help of positive edge triggering, right? So that is the most important. Let's start our journey with this one. You can do it by yourself if you want, right? Let's start. So let us take positive edge triggering. Let us consider some clock pulse in order to get the clear idea, in order to understand these things, right? So let me demonstrate these things with the help of clock pulse, right? So let me do it, right? So let us try and understand these things simply. Let's see. 1, 2, 3, 4, 5, 6, 7, 8. Fine. See there. Positive edge triggering. Positive edge triggering means whenever in our clock our value is goes from 0 to 1, immediately what will happen? Your flip flop will be triggered. That is simply called positive edge triggering. Of course, that is simply called positive edge triggering, right? So let's start our journey with this one, right? So this is the point where we are going to trigger the flip flop. This is the point where we are going to trigger the flip flop, right? Yeah. So simply try and understand, there are no big things, right? Now first step what we need to do, we have to draw the waveform for Q2, that is the output of the first flip flop, right? Now initially all the flip flop values were assumed to be 0, right? All the flip flop values were assumed to be 0, right? So let us see, when we are triggering the flip flop with the help of the clock, now what will happen? See there, this is called toggling mode, right? So this mode of the flip flop is simply called toggling mode. Already we have seen it, right? So toggling mode in the sense, the output of the flip flop is keep on changing with respect to the clock, right? For each and every clock there will be a change in the output, right? If it is in 0, when we are giving the first clock, its value is raised to 1. Again when we are giving the second clock, again this value will be raised to 0, again 1, again 0, again 1, again 0. So whenever we are giving clock pulse, that is the point where your output of the flip-flop is keep on changing with respect to the input as clock, right? So let us see, when we are giving the first clock, immediately the output of the first flip-flop, right, will change from 0 to 1. Again while giving the second clock, positive edge triggering, right? Again while giving the second clock, once again what will happen, it goes from 1 to 0, again it goes from 0 to 1, again it goes from 1 to 0, again it goes from 0 to 1, again it goes from 1 to 0, again it goes from 0 to 1, again it goes from 1 to 0. It's keep on continuous. Now output of the first flip-flop will going to act as a clock of the second flip-flop. Now let us see when this flip-flop will going to be triggered, right? Of course this is the output of the first flip-flop, right? So this is 0 1 0 1 0 1 0 1 0. Now output of the first flip-flop will going to act as a clock for the second flip-flop. Let us see now what type of triggering that we are giving here. This is called positive edge triggering, right? It means whenever output of this flip-flop, first flip-flop, is goes from 0 to 1, that is the point where the second flip-flop will be triggered. Just to forget about the first flip-flop, treat this one as the clock, right? Trigger the second flip-flop. Let's see what happened. Anyway, initial value were assumed to be 0. Now whenever, right, this is the clock for the second flip-flop. Now whenever your value is goes from 0 to 1, immediately second flip-flop will be triggered. Let's see what will happen when we are giving, right? So first flip-flop, that is initial value were assumed to be 0. Now when we are giving the first clock, it value is raised to 0 to 1. Immediately it value is raised to 0 to 1, right? Now it will be continuous until the arrival of next clock pulse. See there, this is the point. Again your clock is going from 0 to 1, right? Once again your output will change from 1 to 0. Again next clock pulse, so it raising its value from 0 to 1, again 1 to 0. It's keep on continuous. Now see that this is 0 1 0 0 1 1 0 0. Now let us see. Now output of the second flip-flop will going to act as the input of the third flip-flop, that is clock of the third flip-flop, such that in order to trigger the third flip-flop, once again if you observe this one, that is positive edge triggering, whenever your clock pulse, right, raising its value from 0 to 1, that is the point where your flip-flop will be enabled or triggered, such that initially the value of the flip-flop is 0. When we are giving the first triggering, immediately its value is raising, right? It's raising its value from 0 to 1, and then it will be continuous until the arrival of the next clock pulse. This is the point. Again we are giving the clock pulse, so it's going down, right? Again it is continuous up to until the arrival of the next clock pulse, such that it is going to be 1 1 1 1 0 0 0 0. Clear? Now if you observe these outputs carefully, see that its count is what you have to start from. This is Q1, this is Q0, right? So let me make the tabular column. Let us consider the clock pulse, and we need to consider Q0 first, Q1 first, sorry, Q2 second, Q1 second, Q2 third, right? Such that at the 0 clock pulse, initially all the bits were assumed to be 0. Now when I am giving the first clock, right, there will be a preset, right, such that your values are going to be what, right, going to raise either 1 1 1. Next while giving the second clock pulse, right, they are going to 1 1 0, right, they are going from, that is while going from first to second clock pulse, automatically this value will be reduced to 1 1 0. Now while going from second to third clock pulse, its corresponding value become 101, right? See there, third clock pulse will become 101. Now while going along with the fourth clock pulse, this is become what, 100, right? So while giving fourth clock pulse, this is become 100. Now while giving fifth clock pulse, which is become what, 011, so it is become 011. While giving sixth clock pulse, this is become what, 010, right? This is become 010. Now while giving seventh clock pulse, which is become what, 001, 001. Now while giving eighth clock pulse, we are getting back to 0. We are getting back to 0. That is, while giving eighth clock pulse, this is going to be the eighth clock pulse. Totally how many flip-flops, that is how many clocks should be required in order to count these 8 states, right? Totally I am in need of 8 clocks. I am in need of 8 clocks, such that we are counting all values, right? Now that is how we are designing the counter circuit. Anyway, it is called asynchronous counter, that is no. Now the conclusion is, now if you observe this one, whether it is acting as a up counter or down counter. Now from this observation, if we are finding the decimal equivalent of these variables, they are going to be what? See there, while giving the first clock pulse, its equivalent value is 7 and then 6 and then 5 and then 4 and then 3 and then 2 and then 1 and then getting back to the initial is 0. Now if you observe this one carefully, my value is going down. That is called what? Descending, right? Values are decreasing. That is called down counter. It is called what? Down counter, right? That is mod 8 down counter. Name of the counter is what? Mod 8 down counter, right? Of course, that is correct. Now, next thing what we are going to design. Suppose, again, I would like to consider same positive edge triggering only. There will be no changes, but I would like to change the position of this one, right? I would like to change the position. That is, instead of traveling from this point to this point, I would like to travel from this point to this point. Let us see what will happen. If I will travel from this point to this point, again, your second, third flip-flop also will going to be enabled from Q bar. If you are doing like that, then what will happen in the output waveform, right? So let's see what will happen now. Yeah. So wait 1 second. So let us remove these things now. Once again, we are going to consider. You please do it by yourself, because now you all have understand these things. I know, right? Yeah. Let us design the next clock pulse. I did not calculate the frequency at all, because same thing you are going to observe: frequency, duty cycle, right? Everything we learned already, right? So same thing we are going to observe here. That's why I did not calculate it, right? Okay, fine. So we design. Once again, we saw how to design mod 8 counter, right? Next, what we are going to do? The next task is, let us consider. Once again, we are giving positive edge triggering only. So let me consider 8 clock pulses. 1, 2, 3. We are going to consider 4th clock pulse, 5th clock pulse, 6th clock pulse, 7th clock pulse, 8th clock pulse, and so on. Clear? Yes. Now again we are going to provide what? Positive edge triggering. It means whenever your value is going from 0 to 1, 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 there will be a change, right? Because our system is what? Toggling. Nature of the system is toggling, right? Toggling in the sense, what will happen? See there, let us assume the initial is 0. Initial is 0, right? Initial is, okay, let me slowly draw the clock pulse pattern. You please wait, right? So the thing is, wait, let me complete. Okay, let's start our journey with the first one. The first one is what? Initially we were assumed to be, right? Assume all the values are 0, 0, 0 only, right? Such that we can say the value of Q2 and the value of Q1 and the value of Q0 all are going to be 0, right? This is Q2. Now let us see what happened. When we are giving the first clock pulse, automatically it will be raising its value from 0 to 1. Again it is going back to 1 to 0, again 0 to 1, again 1 to 0, again 0 to 1, again 1 to 0, again 0 to 1, again 1 to 0, and so on. Now let us see, this is 0, 1, 0, 1, 0, 1, 0, 1, 0, 1. Yeah. Feeling happy, right? Now the second thing is, output of the first flip-flop will going to act as a input of the next flip-flop, right? Now what you are trying to conclude here, if you observe these things carefully, right? Actually see there, Q1, right? Which is Q1 here? Q1, guys, listen carefully, observe. This is the output of the first flip-flop, whereas your second flip-flop will going to be triggered with the help of Q2 bar, not with the Q2. You'll have to understand, it will be triggered with the help of Q2 bar, not with the Q2. Now what I need to do, so let me draw the Q2 bar also, right? 1 second, let me rub these things. So let us rub this one. Now let us design Q2 bar first, because Q2 bar will going to act as the input of the next flip-flop, right? If Q2 bar is going to act as the input of the next flip-flop, then what will happen? Let us see. Just to see that this is Q2. Q2 bar, in the sense you'll have to take, and that is complement for this one, such that 0 will become 1, 1 will become 0, 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 0 will become 1, 1 will become 0. It will go like this. Now if you observe, see there, complement Q bar, in the sense, in Q bar, whenever Q is going from 1 to 0, that is the point your Q bar is going from 0 to 1. So hereafter you don't need to draw this pattern separately. You just think like this. If you are taking Q bar as the flip-flop input, that is clock of the next flip-flop, we can directly say, you can directly take Q2, but Q2 bar, in the sense you'll have to go from 0 to 1. Instead of going with this one, you can directly take Q2. See there, at the same point, Q2 is going from 1 to 0. Q2 bar is going from 0 to 1. Actually, this is the clock for us. Instead of going with the Q2 bar, right, unnecessarily, you don't need to draw this pattern separately. Directly, you can consider Q2 bar in the sense, if it is going from 1 to 0, next flip-flop will be triggered. 1 to 0, next flip-flop will be triggered. It does not mean that we are considering negative edge triggering. No, no, no. I'm not telling like that. Q2 bar is producing opposite to this one. It is opposite to this waveform in the sense, whenever it is going from 1 to 0, it will become 0 to 1. So instead of considering this one, you can also consider this one. That is what I would like to conclude, right? So let us draw the waveform, right? So hereafter, let me remove this one, right? So let us draw the pattern for this. Now what we have understood, right? So from this Q2, I don't want Q2, we are considering Q2 bar. If Q2 bar in the sense, we have to consider 1 to 0 as the clock. Let us consider the next one output, Q1. Initially 0, it will be continuous. It is 0 only. Whenever your Q2 is going from 1 to 0, that is the point it will be triggered, right? Again, it is going from what? Where it is going from 1 to 0, this is 1 to 0. Again, it will be triggered. Again, where it is going from 1 to 0, again it will be triggered. Again, where it is going from 1 to 0, again it will be triggered, and so on. Clear? Now, once again, Q1 is not going to be the clock of the next flip-flop. Q1 bar is going to be the clock of the next flip-flop. Such that Q1, actually we are considering positive edge triggering. It means we need to consider 0 to 1 as the input, right? 0 to 1, but what? 0 to 1 of Q1 bar. So 0 to 1 of Q1 bar will be equal to 1 to 0 of Q. Both are a complement of each other, na? So the conclusion is, whenever it is going from 1 to 0, whenever it is going from 1 to 0, your next flip-flop will be triggered, right? So let's start our journey with the initial value. Once again, Q0 is going to be 0, 0. See there, whenever it is going from 1 to 0, that is the point where it will be triggered. Again, whenever it is going from 1 to 0, that is the point it will going to be triggered. Now, if you observe carefully this one, 0, 0, 0, 0, 1, 1, 1, 1, and this is become 0, this will be 1. Just extend this one, right? Yeah, I think I put all values. Shall we start our journey now? Right, let's see what will happen. See there, initially we have, prior to the application of clock, we have 0, 0, 0. Now, when we are applying first clock, we got what? 0, 0, 1. Again, second clock, 0, 1, 0. And then 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. What is this? It is in ascending order, like we are starting at 0, 1, 2, 3, 4, 5, 6, 7. What is this? Up counter, right? Of course, it is called up counter. Of course, it is called up counter, right? So this is simply called mod 8 up counter. The name of the circuit is what? Mod 8 up counter. Simply we can name like this, right? So finally, what we have understood here, we can design either up counter or down counter, whichever the things that you want, you can simply design with the help of flip-flop circuits. But we understood one thing. See there, here I had applied positive clock, whereas your next flip-flop will be triggered with the help of Q2 bar. Suppose, right now, right? So let me write. The clock is, right? Let us see the relation. Clock, right? So in clock, there are two cases. Either you can consider positive edge triggering. Either you can consider positive edge triggering, right? Let us consider there are two cases. Positive edge triggering. And you can also consider negative edge triggering, right? There are two cases in negative edge triggering also. There are two cases in negative edge triggering, right? Now, when your second flip-flop, right? So a second flip-flop will be enabled with the help of, see there, positive edge triggering that we are considering Q2, Q bar, right? Positive edge triggering, and we are considering Q bar as the clock of the next one, right? If you are considering Q bar as the clock, automatically this counter combination will act as a up counter. This counter combination will give us up counter. Whenever we are considering positive edge triggering only, but for the next flip-flop, we are considering Q2 as the clock, right? That is Q as the clock. In general, if you are considering Q as the clock, then automatically it will act as a down counter, right? So it will act as a down counter. I hope that portion is visible. Let me check it by myself once. Yeah, that is visible, right? Now, when we are considering, see there. Now, again see there, positive edge triggering, Q bar will act as a up counter. Then negative edge triggering, Q will act as a up counter. Once again, negative edge triggering, Q will act as a up counter. Whereas negative edge triggering, Q bar will act as a down counter. Will act as a down counter. You can just cross check it by yourself. Just make it as a tabular column, because that is the most important observations that we are getting from this circuit. Just by observing the circuit itself, you can tell whether the circuit is up counter or down counter just by using these two things, right? If you observe this one, right, see there, positive edge triggering with the Q is always down. Negative edge triggering with the Q bar is always down, right? So let me repeat. Positive edge triggering with the Q, negative edge triggering with the Q bar. same value. See there, bubble means negative, q bar means negative. So negative negative will give you down, positive positive will give you down, opposite will give you up. Opposite means, see there, positive q bar is opposite. Positive means that is positive, q bar is complement, not negative. Just keep like this. This is negative, this is positive. Positive negative will give you up counter, positive positive will give you down counter, negative negative will give you down counter, negative positive will give you up counter. It means opposite people, like q bar positive will give you out, that is up counter. Q negative also will give you up counter. Negative negative, positive positive. This is positive, this is positive, this is negative, this is negative, simply acting as a down counter. That's all. Just do remember this one. That is the most important observation, right? Because with this only you will be able to identify whether the given circuit is up counter or down counter. Clear? So till now what we saw how to design the counter circuits, right? Of course they are all called binary counters. Like binary counter in the sense, we should start with a 0 and you'll have to travel with a proper manner. Like either you can travel in ascending order or you can travel in the descending order, right? So we can start from 0 1 2 3 4 5 6 7, or you can come like this 7 6 5 4 3 2 1, right? So that is the standard binary order, right? Now let us design the one more type of circuit, that is called non-binary counters, right? So they are simply called what? Non-binary counter, right? Of course there will be some another name for this type of counter. They are called what? Ripple counter, right? So they are ripple in nature, right? So these counters are called what? Ripple counter. So you can simply call them, whichever the counter that we design, they are simply called what? Ripple counter. There will be one more name for this one, right? Fine. What is our next task? Now we are going to design non-binary counter. Okay guys, since we are lying under asynchronous counter only, right? So there are two type of counter. One is called synchronous counter and another one is called asynchronous counter, right? Basically simply just by looking at the circuit itself we can guess it whether it is synchronous or asynchronous. Synchronous in the sense all the junctions will be synchronized together, like our what I can say in train, like that is what I have been told you. Just your train, all the boxes will be synchronized together. If your first box will move, immediately all the box will move, right? That is our train. Like synchronous counter in the sense all the flip-flop will be enabled with a single clock, right? If you observe asynchronous counter, see there second flip-flop, they are different clock pulse. First, this is our original clock, but this original clock will activate only first flip-flop, whereas the rest of flip-flops are being enabled with the help of the output of the remaining flip-flops. This is not synchronous counter. Synchronous in the sense all the flip-flop will be synchronized with a common clock. Clear? Let's see. Anyway, we are in asynchronous counter. This is the basic binary counters. Now let us design the non-binary counter, right? Non-binary counter in the sense what I can say, for an example, this is 0 to 7 we design, that is called mod 8 counter. Now in if you want to design mod 6 counter, like it is not a proper value. It means, listen guys, mod 2 counter we can directly say from the 2 power n combination. If I put n equal to 1, then with the help of 2 flip-flop we can design what? If see here I took 3 flip-flop, we can design mod 8 counter. It means 2 power 3, right? We are bringing 8 states. If you want to bring 4 states, then at least you need of how many flip-flops should be required? 2 flip-flop, because 4 states in the sense you should consider 2 power 2, where 2 power 2 n, 2 power 2, that 2 denotes number of flip-flops, right? 2 power n, see that 2 power n. If I keep n equal to 2, such that, see that we can create 4 states like 0 0 0 1 1 0 1 1, right? So those 4 states could be possible with the help of what? This is called what? Mod 4 counter. In order to design the mod 4 counter, how many flip-flops should be required? This is called number of flip-flops. We all know this is called number of flip-flops, right? So to bring 4 states, that relations already I have written is right? I have written these things. So the conclusion is what? In order to bring the 4 states, I am in need of 2 flip-flop. In order to bring the 8 states, if I keep 2 power 3, it will give you 8. In order to bring 8 states, I am in need of 3 flip-flops. In order to bring 16 state, I am in need of 2 power 4 flip-flop. Now the question is non-binary counter in the sense any values, like if you want to design mod 5 counter, mod 6 counter, mod 9 counter, mod 11 counter, mod 14 counter, mod 32 counter, mod 31, like 19. How will you design those type of counter? They are simply called a non-binary counter, right? So because they are not binary count, right? So binary count in the sense we should raise our value like 2 power 1, 2 power 2, 2 power 3, 2 power 4, 2 power 5. They are called what? In that order. 2 power 2 in the sense 4, and then 2 power 3, 8, 2 power 4, 16, 2 power 5, 32, and then 64, 128, 256. They are simply called what? Binary order, right? So let us design non-binary counter. Yeah, let me rub these things, right? So let us design non-binary counters. Keep the heading. We are going to design non-binary counters, right? See, that is very easy, guys, right? You can visualize these things, right? I'm not lying. See how much easy your circuits are. You can design it by yourself. So you'll make some mistakes at this point, you can identify it. That is all about digital electronics. There are no things to learn new, right? Just you'll have to understand the logics and you can apply it. Automatically answer will fall in down, right? Fine. What we are going to design, we are going to design okay, that things I don't want to know, we can remove it. Let us design non-binary counter. Next we are going to design non-binary counter. So let us design non-binary counter, any counting, right? Now let us see how to design some general counter circuits, right? The first thing is, it's quite interesting actually, right? In order to design the non-binary counter, first of all we need to understand the difference between clear and preset, right? Clear and preset. Clear and preset, that is the most important thing to understand here, right? So similarly we just what do you mean by clear, what do you mean by preset? Clear means, right, your output is going to be 0, that is we are clearing the outputs, right, such that output of the flip-flop is going to be 0. Preset means preset will going to set the output value as 1, right? That is the difference between clear and preset, right? Let me repeat once again. Clear means output of the flip-flop is going to be cleared as 0. Preset means output of the flip-flop is going to be set its value as 1. That is called a preset, right? So that is called preset, and this is called a clear pin. So we are going to use two type of pins in our counter circuits. Either you can use preset or you can use clear. It depends on the type of the application that we are going to use. Now the question is, for which circuit we are giving priority for preset, for which type of circuits we are giving priority for clear pin, right? Now if you observe, we had been designed two type of counter. One is called up counter and another one is called down counter. Now what do I mean by up counter? Up counter count its value from 0. So the initial value that it should be required in case of up counter is 0. Whenever we are looking for up counter, we are starting at 0 0 0 and then we are raising our value up to 1 1 1. It's based on the number of flip-flops that we are considering. For 3 flip-flops we can go from 0 0 0 to 1 1 1, such that when we are designing the down counter, you will have to start your value at 1 1 1 and you will have to continue your journey up to 0 0 0. Now if you want to design the down counter, the initial states required as is 1 1 1. Now if you want to design the up counter, the initial state is what? 0 0 0. That is the difference between up counter and the down counter. Just apply this logic here. Now whenever, see there, initial state, right? For which type of counter I am in need of initial state as 0. For up counter I am in need of initial state as 0. So clear pin should be used as, that is should be used in up counters, right? Clear pins would be used in up counter. Similarly, where we are going to use preset, just observe this one. This is down counter. In case of down counter, output I am in need of what? 1 1 1, right? So output 1, initial state, right? So initially if you want to 1, then the correspondent logic is called preset. So preset only will going to set the output value as 1, such that this type of counter, right? So preset will be used in what? Down counter. So preset application, we are going to use it in down counter, right? We are going to use it in down counter. That is the next thing that I would like to consider, right? And the next thing is, in order to work your preset, work along with the preset, right? The input for your preset is 0 and the input for your clear is 1, right? The input for your clear pin, right? For the clear pin you'll have to apply 1 as the input. For the preset pin you'll have to apply 0 as the input, right? So you'll have to apply 0 as the input, right? So let's continue our journey with this. Now what type of gates that we are going to use for this? Logically we will learn these things basic, right? With the basics you will see slowly, right? So let me remove these things, right? You can understand, right, later. Okay, fine. So let us design the circuits. Now what I am going to do, for an example, I would like to design mod 6 counter, right? So basically, understand, guys, listen. Now what do we mean by mod 6 counter? Mod 6, let us assume mod 6 up counter. I would like to design mod 6 up counter. I would like to design mod 6 up counter. Now in order to design mod 6 up counter, first of all we are designing what? Up counter. Up counter means we use our pin as clear pin. The type of pin that it should be required in order to design is either you can use clear or you can use clear bar. It's your wish. You can use clear or you can use clear bar, right? So both of this type of logics could be applicable. We will see, right? We will see later. We will understand this difference between these two guises, right? Okay. Anyway, in order to design the up counter, I made of clear pin. First thing, right? And the next thing is we are going to design mod 6 counter, up counter. Up counter in the sense it will start counting from 0 0 0. Next state will become 0 0 1. Next state will become 0 1 0. Next state will become 0 1 1, and then it will become 1 0 0, and then it will become 1 0 1. How many states are there? State 1, state, that is state 1, state 2, state 3, state 4, state 5, state 6. Now immediately when we are getting 7th state, that is the point where your input, that is output of the flip-flop, will going to be cleared, right? Output of the flip-flop will going to be cleared when its output will become 1 1 0. This is not the acceptable states, whereas rest of all states are acceptable states. See there again, let me repeat once again. We are designing mod 6 up counter. Up counter means initial state of the up counter is 0 0 0. Then it will start counting 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 1 1 0 1. Up to that there is no issues with our output states, because this is possible outputs, that is what we are looking for in case of mod 6 subcounter. But when I am getting the 7th state, that is the point, immediately your clear pin will work and it will reset, it will set the output, that is it will clear the output values as 0 0 0 0, such that, right? So we are getting back, such that we are getting back to the, what I can say, initial state. Clear? So that is how we are designing what I can say, mod 6 up counter, right? So in order to design the mod 6 up counter, let us consider its correspondent logic, right? So now what is the conclusion here? We are going to consider mod 6 up counter in the sense, let me name them. This is Q0, Q1, this is going to be Q2, right? Q0, Q1, Q2. Now at which pin we are going to set? See there, exactly when we are getting 1 1 0, right? For Q0 we have to get 1, for Q1 we have to get 1, for Q2 we are going to get 0. This is the point where we are going to reset, that is we are going to clear the flip-flop, right? Clear the flip-flops, right? So let us take the circuits first, right? How many flip-flops should be required? The number of flip-flops should be required in order to design the circuit is, we have seen the relation is 2 power n greater than or equal to number of states, right? Now here in order to design the 6, right, in order to consider the 6 counters, I cannot consider n equal to 3, n equal to 2 means we are going to get only 4 states. When I am putting n equal to 3, we are going to get 8 states. Possibly in 8 states we can bring the 6 states, that could be possible, right? So n equal to 3, I am in need of 3 flip-flops. The minimum number of flip-flops that it should be required is 3, right? So the number of flip-flops that we are going to use is simply called 3, right? Now let us see how to design these things. Now from here let us consider once again, anyway we are designing counter circuits, so either you can consider T flip-flop or you can consider JK flip-flop. If I are considering T flip-flop, T0, T1, T2, right? So this is going to be Q2 and this is going to be Q2 bar, and this is going to be Q2, once again this is going to be Q2 bar, again this is going to be, sorry, this is Q1, right? Q1, Q0 bar. Now see that they are going to be the outputs of the flip-flop. This is going to be the output of the flip-flop. Now for all the inputs, right? So flip-flop inputs are going to be assumed to be what we are going to provide, right? That is the input of the flip-flop is what? 1. Because this is T flip-flop now, we have to keep them in what? Toggling mode, right? So we should keep them in toggling mode. That is the most important thing, right? So anyway, since we are designing what? Up counter, right? So we are designing up counter in the sense, right? So there are 2 type of possibilities will be there. Suppose if you are going up with a negative edge triggering, up counter in the sense, in order to design the up counter, see there, if I'll give negative edge triggering, right, then you'll have to consider Q as the output. That is Q is going to be act as a clock of the next flip-flop. Again that is negative edge triggering, na? Yeah. Again this one will going to consider the blob. This is up counter. First we are designing. This is possible. This is also correct. This type of combination also correct. Either you can go up with any one, right? So anyway, now up to now everything is perfect. So now this one will act as a what? Mod 8 up counter. See there, 3 flip-flops are there. It will act as a what? Mod 8 up counter. But I don't want mod 8 up counter. I would like to count only up to what? For 6 states. Right, after reaching 6th state, that is 6th state, immediately in the 7th states in the sense what? See there, when this is Q0, when Q0 is going to be 0 and Q0 is going to be 1 now, 1 1 0, right? This is 1, this is 1 1 0. right? Immediately when we are getting this state as the output, that is the point where we have to what I can say, clear the output pin such that immediately it will become 0 0 0. Whenever we are getting this state, immediately it will be cleared, because see there 1 1 0, that is the 6th state, unacceptable states. For the rest of states there is no issues, but this state is not acceptable, right? So now what we have to do, yes, immediately when we are getting these states, immediately we'll have to clear the pin, right? So in order to clear the pin, right, either we can use, right, so we are going to use two type of gates, right? Either we can use NAND gate or AND gate. We can use NAND gate, or you can use AND gate also, or you can use OR gate, or we can also use NOR gate. There are four type of gates that we are going to use here, right? So we are going to use 4 type of gates, but priority will be given, right? So whenever we are designing, right, so if we are designing, I will conclude, right, whenever we are using that is up counter, we are going to use what, clear and clear bar pins, right? So clear means input of the clear pin must be what, 1, whereas clear bar means input of the clear bar pin must be 0. Clear? So if you are giving 0, then only it will be clear. If you are giving 1, it will be what, once again it will be clear. This pin will work when input of clear pin is going to be 1. This pin will work when input of this one is going to be 0, right? Such that I am introducing one more pin here, that is simply called clear pin. So let us use clear first. Let us use clear pin simply, right? So this is called simply clear pin. Clear bar means you will have to put inga represent pannirupanga, right? So it will be represented with a bar potrupanga, right? So anyway, simply we are using clear only, right? So in this clear pin, what we are going to do, so first of all, let us join all this clear pin together, right? So first of all, we need to join all these clear pins together, and then let us consider. The thing is, I said either we can use NAND gate or AND gate, right? So let us consider the NAND gate and AND gates here. Let us consider AND gate. Let us consider NAND gate also. Let us consider NAND gate also. Now here the select the high pins, right? So நீங்க clear பண்ண போறீங்க இல்லையா, அந்த clear பண்ண போற இடத்துல உங்களுக்கு இருக்க states இருக்கு இல்லையா, அந்த states வெளியில எடுத்துக்கிட்டு அதுல வந்து just select the high values னா 1 1, right? So here correspondent Q0 Q1 are producing 1 1, right? So Q0, from Q0 we are getting 1, that is, let me consider Q0 value as 1, and Q1 also producing 1 na. Yes, see, if you are giving 1 1 to the AND gate, output is going to be 1, whereas if you are giving 1 1 to the NAND gate, output is going to be 0. Now just to see that one here, what I am going to do here, let me take one output here. I am just taking the output from here, and let me rub these things. Slowly observe. There are no big things to understand, right? Actually we have to clear the circuit at a 110 state, right? We have to clear the circuit at a 110 state. It means just where we have 1 at Q0 we have 1, at Q1 also we have 1, right? So I'm just considering those two states, right? I'm just considering those two states. Now the question is whether we need to use right which gate should be required here, right? Which type of gate should be applicable? Either we are giving priority for AND or NAND gate. The thing is, for clear pin, clear means input of the clear pin must be 1. I mean of 1. Now tell me, there are two gates. Which gate will give you output as 1? AND gate, right? Immediately, right? If you are giving 1 1 to the NAND gate, output will become 0, right? So what is the conclusion here? You will have to consider AND gate here. You will have to consider AND gate such that this one will come here. Output is going to be 1. They will clear the pin. Now this circuit will act as a mod 6 counter. When 1 1 will come, right? 1 1 on the immediately all the values are going to be cleared such that 0 0 0 will appear. Again they will start at counting from 0 0 0 and then 0 0 1 0 1 0 0 1 1 1 double, that is 1 0 1, and then when we are getting 1 0 1 and the next state is 1 1 0. When we are getting 1 1 0, immediately again reset. It will continue its operation. That is how we are designing mod 6 counter. I hope things are very clear to you all. Anyway, what we have designed here, we design mod 6 up counter, right? In the same way, suppose if I am putting, this is one type of circuit, right? Just treat this one as the model 1. Now you please draw the circuit separately. If you want to design the second type of circuit, that is, I would like to use clear bar in the sense, let me place clear bar here. Let me remove this one. Clear bar, this is also going to be clear bar. For clear bar, the required input is 0. We have to apply 0. If you want to apply 0, then which type of gate should be required here? We have to use NAND gate. If you are using NAND gate, automatically what will happen? For this, with the help of NAND gate, we can provide what? If you are passing 1 through the NAND gate, automatically output will become 0, such that your circuit won't work, right? That is, your circuit will become what? Once again, it will clear the output, right? So what is the conclusion, guys? If you are using clear bar, that is a clear and a clear bar. There are two type of circuit, right? For clear and a clear bar. Now let me fix all these things, right? For clear pin, if you are using clear as the input pin, right, then you are requested to use AND gate as the that is correspondent logic, right? If you are using clear bar, then we can use NAND gate as the input, right? Then we can use NAND gate, right? Such that it will helping us to fix the outputs, right? So let us see, when we are looking for down counters, I would like to design mod 6 down counter, right? So let us design the mod 6 down counter. Yeah. Keep that ding. Now we are going to design mod 6 down counter. Now how to design the mod 6 down counter? In order to design the mod 6 down counter, let us see mod 6 down counter, mod 6 down counter, right? So this is going to be mod 6 down counter. Now mod 6 down counter, in the sense, what we need to do, first of all, listen, down denotes we have to use what? Preset. Down, either you can use preset or you can use preset bar, because down counter will start counting from 111. Anyway, once again you are requested to design mod 6 down, in the sense, you can start from 111, next state will become 110, next state will become 101, and then 100, and then 011, right? And then 010. How many states are there? 1, 2, 3, 4, 5, 6, right? So totally 6 states. Now when we are getting 001, this is the state, immediately we have to preset. The circuit. Either you can use preset or we can use preset bar, it's your wish, right? But the conclusion is what? When we are getting 001, immediately you have to get back to 111, because we are designing what? Mod 6 counter. Mod 6 means we should travel, you are supposed to travel up to 010. 001 is not acceptable when we are designing mod 6 counter, right? Okay, fine. So anyway, how many flip-flops should be required in order to design the 6 counter? 6, in the sense, we know the combination 2 power n greater than or equal to n, such that if I will consider n equal to 2, then number of flip-flops are 2. If I will consider 2 flip-flops, you can go up to what? 4 states. But I'm in need of 6 states. So let us raise. If I will consider n equal to 3, then we are getting 8, of course. But 8 states not required, right? I'm in need of only what? 1, 2, 3, 4, 5, 6 states only. Immediately when we are getting 7th state, that is going to be what? Preset, right? So immediately that will be preset, means we are getting back to 111, right? Such that I'm in need of 3 flip-flops. Once again, we need to consider 3 flip-flops. Let us consider 3 flip-flops, right? Yeah, wait a minute. We need to consider 3 flip-flops. When we are considering 3 flip-flops, once again we need to design what? T flip-flop, right? So we need to consider T flip-flop, and outputs are going to be Q2, Q1, Q0, right? Our next task is what? We are trying to design, right? Sorry guys. Yeah. So next task is preset. Okay, let us see what we have to design. Down counter. Down counter, in the sense, either see the down counter, let me place it here. See the down counter, in the sense, positive H, positive Q, negative negative, that will act as a down counter, such that if you are providing positive clock pulse, then what will happen? Q2 will going to act as a clock of the next one, Q1 will going to act as a clock of the this one, such that what happen, these all values are going to be 1 1 1. Clear? Okay, next what we are going to do, we have to consider preset, right? So let me consider preset here. Let us consider, okay, first let us draw the preset pins here. Let me join them together, that is going to be preset. Simply let me treat them as preset. Let us consider preset, and here also we are going to consider preset, here also we are going to consider preset. Now in order to, for the preset pin we should pass 0, for preset bar we should pass C, for the preset pin we should pass 0, for the preset bar we should pass 1, right? So let us see how they are going to work here, right? So the conclusion is, once again, 001, this is the point. See there, once again select the high value, they are going to be Q0, Q1, Q2. Now high value is Q2 only. Q2 is where this is Q2 and its value is going to be, we are simply treating this value as 1. This value is going to be 1, right? Now what type of gate that we are going to consider, right? In order to design the preset circuits, right, either you can design NOR gate, either you can design NOR gate, or you can also design OR gate. You can also use OR gate, it's your wish. You can use NOR gate, you can use, or you can also use OR gate, right? You can use you can also use OR gate, right? So let us see what will happen here. Suppose if you are, this is 1, right, this is going to be 1, right? If you are not considering this one, you can also consider 0 0. It's up to you. Anyway, just to listen here, if I just consider, okay, let me take 0 0 also. If this is going to be 0 na, if it is 1, then remaining two states are going to be 0. Q0 and Q both are going to be 0, such that what will happen, see there, for preset I am in need of 0, right? If I use OR gate, then what will happen? If you are using OR gate, let us see what will happen. If you are using OR gate, then automatically what will happen? Output is going to be 0, right? Output is going to be 0. If you are using OR gate, then output is going to be 0, right? Automatically what will happen? 0 plus 0 will going to give us 0 only, right? Suppose you are not taking this one, right? You are taking 1, like last case number 1, same case you can consider. If you are taking 1, then both OR gates, right, just join like this. Now what will happen? See there, let me consider like this. It will be synchronized. This 1 is giving as a input for your OR gate, such that 1 1 will give you 1, but I don't want 1 here, right? I don't want 1. Then what we need to do? We have to consider NOR gate. If you are considering NOR gate, now while giving 1 1, output of the NOR gate is going to be 0, such that preset pin will work, right? Preset pin will work. Automatically what will happen? It will clear the set. Whenever it is going to be, when it is going to be 1, automatically what will happen? That is the which state? When this person is, that is this person alone is going to be 1. Rest of 2 people are going to be 0. That is the point where your flip-flop, that is counter, will work once again. And what will happen? It will that is preset the circuit as 1 1 1. It will preset the circuit as 1 1 1. That is how we are designing what I can say mod 6 subcounter. You can also reverse this process, right? Reverse in the sense, instead of considering preset, right, you can also consider preset bar. If you are considering preset bar, then input should be recorded as 1. If it is 1, then here I am in need of OR gate only. Directly you can consider OR gate and you can design the circuit, right? So totally we can use what? NAND gate we can use, AND gate we can use, NOR gate we can use, OR gate we can use. But the thing is what? If you are discussing about preset pin, then we need to talk about OR gate or NOR gate. If you are discussing about clear pin, then we need to talk about NAND gate or AND gate. Either you can consider NAND gate or you can consider AND gate. Clear? You can either you can go up with this one or you can go up with this one, right? So that's all. There are no more things to learn from this. Guys, don't forget this logic, because in your examination you'll be tested for some worthless 2 more questions. But the issue is, right, without knowing these logics, if you're observing the circuit, you don't get the answer. You won't get the answer. So automatically you'll be troubled, right? So should try to understand these logics. That is enough, right? So let me give some tables column, that is I designed already. So let me post them here, such that you will get the clear idea, right, regarding the circuits, right? So let me remove these circuits now. So let me post that one here. Let me tell you some common logics, right, regarding the circuits. Okay, first of all, I saw some questions. I will solve that question here. You please tell me the answer. Actually, there is a counter is given to us, right? So let us take the questions first, and then I will give you that common logics that might be better than this one, right? You will get clear idea. In the question, they are given 3 flip-flops, right? They are given 3 flip-flops, and you are requested to find out the mod of the counter, right? So let us that is the given circuit. The ripple counter shown in the figure work as a, that is the question, right? And this is given as preset. Of course they are using preset, right? Preset. Here also we are going to use preset, right? We are going to use preset, right? In this preset, right, what we are going to see now, let me wait 1 second, right? So let me complete all those things. Yeah, it will be like this. And let us give this one, right? So let me take this one. Yeah, okay, we can do like this, right? Now next they are giving one more clock, right, like this one, right? Positive clock, and they are using T flip-flop, right? So T means all the values are going to be 1 1 only, na? So they said that is 1, this is 1, this is 1, right? And with this they are using few more things, right? They are taking the outputs of this one, right? 1 second, let me consider. They are taking the output from here, This is what? This is Q2. This is Q2 bar. This is Q2 bar. Let us consider. Very simply you can observe, right? You no need to consider anything here. If a logic circuit is given, directly you can post your answer. You no need to solve anything, right? Let me show you how to do that one, right? Again, they took one more pin from here, right? And they join all these things together, I think. That's all. I think they took this one also, right? They took this one also. Let me consider here. They took one more pin from here, such that all these pins are synchronized together with the AND gate, right? They put AND gate here. Then what they have done, actually they took preset pin. This is preset pin. Now let me join them together. It will be synchronized like that. That's all. That is the given circuit. And you are requested to find out the, they are given 4 options. That is mod 3 up counter, mod 3 up counter. The question is mod 3 up counter. And let me take the second one. The second question is mod up 5 counter, mod up, that is mod 5 up counter, mod 5 up counter, right? And third circuit they said, right? Third circuit is mod 3 down counter, right? The third circuit is mod 3 down counter, right? So they said that is mod 3 down counter, right? And in option D, they said mod 5 down counter, that is going to be mod 5 down counter, that is going to be mod 5 down counter. Okay, fine, that is over. Now what we are going to do with this, right? The conclusion is we have to identify the type of the what type of counter it is. Guys, it is very simple. You don't need to follow any logics here, right? See, now the procedure that I taught in the previous case, we have to design this circuit from the given question. Suppose if you are requested to find out the mod 5, mod 6 like that, then you can proceed like that, right? But directly these type of questions only, most of the cases, mostly in your examination, you'll be tested with these type of circuits. Circuit will be given to you and you are requested to find out the type of the counter. First of all, tell me whether it is up counter or down counter. Is it up counter or down counter? The logic is, see there, given it is positive logic. That is, they are giving what? It is what? Positive edge triggering. First I think it is positive edge triggering. And the output is, see there, they are taking Q2, that is Q as the clock. Q is going to act as a clock. Now see there, positive edge triggering, where is positive edge triggering and the Q is acting as a clock, such that it will act as a down counter. So we can remove 2 options from here, right? It is going to act as a down counter. So we should find one thing here, concluded. Second thing is, now the question is either it is 3 or 5. We need to find only this one, right? See there how simply we are solving. We are getting 2 marks, right? Worthless. Let's see. The thing is, see there, we are looking for preset pin. Right, see there, let me synchronize this one. We are looking for preset pin, right? Now in order to get this one, right, in this case we are using AND gate. Now if you are using AND gate, then you'll have to pass to the preset pin as 1. If it is 1, then this all values also going to be 1. If it is 1, then here, see that this 1 will come here, automatically this will be 0, right? See that this 1 will come here, such that here we have 1, right? This 1 will come here, automatically this is going to be 0. If you observe these states, that is going to be what? 0, 1, 0. Actually we are considering 0, 1, 0, right? 0, 1, 0, right? Exact 0, 1, 0 varumbodhu enna irukku, your pins are going to be preset, right? So your pins are going to be preset. Okay, fine. So let us consider, guys, here we are not using OR gate, we are using AND gate, right? So in AND gate your output is what? It is going to be 1, right? So if it is 1, then your preset pins will work, right? So if it is 1, then what will happen automatically? See, you just if your circuit will be given like this, you just keep like this. If you have bar here, then pass 0, right? In logic, general logic, circuit will be given. If circuit will be given, don't consider this what type of gate at all we are passing here. Just general logic is, for preset we have to pass 1, for clear pin we have to pass 1, bar we have to pass 0, for bar we have to pass 0. In general, just you can keep that one and you can find out the answer for this type of general circuits. Because see there, for preset we are using what? AND gate here, right? So let us see how we are going to find out the answer for this one. Anyway, our answer is what? We can simply say, here we are getting at 0, 1, 0. This is the stage where we are trying to clear the, that is preset the pin, right? It means we have started our journey at 1, 1, 1 and it is continuous 1, 1, 0, and then we are traveling up to what I can say, let me consider 1, 0, 1, 1, 0, 0, 0, 1, 1, and then this is the point when we are getting 0, 1, 0, that is the point where your pin will going to preset. Preset in the sense it is getting back to the state, right? See there, how many states? 1, 2, 3, 4, 5. So what type of counter it is? Mod 5 down counter. So the answer is what? Option D. Clear? So let me take one more circuit. So let me take one more circuit. I hope things are clear to you all. So let me rub these things. See, while designing the circuits, just do remember the things that I've been taught you already, right? Now, if you are facing this type of questions blindly, just to go with the normal, right? We have to pass 1 in order to activate the pin. We have to pass, that is 0 should be passed in order to complement activate panna, we should pass 0 in order to design the clear. That is, if there is no complement, directly we can pass 1, right? So let me take, that is, let us take the second circuit. Again, they are considering, so 1 second, let me consider the next circuit also. You can design this one also. In general, you can design like this, like they are given 4 circuits. Once again, they are considering T flip-flop only, right? That is going to be T, 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 right? And we are going to consider negative edge triggering now, right? So this is negative edge triggering, right? So this is going to be what? Negative edge triggering, such that they are considering what? They took these outputs, right? All the people, right? I think they are considering all these things. 1 second, let me confirm it myself. No, that is not like that. Actually, they put this one from here, such that they will be joined together, right? As what? With a NAND gate. And we are passing it to, right? For NAND gate, and we are passing it to the what? Bar, right? It is simply, they did not told either they are using preset or a clear pin. They did not told anything, right? They did not told anything. Okay, we don't want to know that one. Just observe what I've been told you. Complement means we need to pass 0. First thing, we need to pass 0. Now I am in need of 0 pin here, right? Just I want 0 here. Now they are given 4 options. Once again, they said mod 5 counter and mod 8 counter, mod 7 counter, like mod 6 counter. I think they are given 4 options. Anyway, now tell me whether it is up counter or down counter. See there, we are giving negative edge triggering and we are taking Q as the output. See there, negative edge triggering, Q as the output, that is up counter. First thing is, this is up counter. One thing we have to visualize, it will act as a up counter. Up counter means its initial state must be 0 0 0, such that we are using what? Clear pin. Clear we are using, right? So for the, in order to activate the clear pin, we should pass 0 here. Of course, this logic is correct. I said either you can use an AND gate or you can use what? AND gate. I told you there are 2 logics, right? Yes. Fine. So this is NAND gate and its output is going to be 0, such that the circuit will be automatically triggered, right? When this output is going to be 0, NAND gate output is going to be 0 when all its inputs are going to be 1. Do you all agree with me? Yes, that is the one and only case where your output of the NAND gate is going to be 0. Guys, listen. Here we are using clear bar pin. Actually, this is clear bar pin. For clear bar pin, we should pass 0. We need to pass 0, right? That is given it is what? NAND gate. If you want to get 0 here, then all its corresponding inputs are going to be 1 1 1, such that here we are getting 1 and this 1 will come here. If it is 1, opposite is 0. Complement of each other, right? Similarly, here also we are going to get 1, such that if you observe the states, we are going up to what? 1 0 1. This is the state where we are presetting. Now what I can say, we have started our journey at 0 0 0, 0 0 1, 0 1 0, 0 0 1 1, 1 0 0. Exactly when we are getting 1 0 1, that is the point where we are clearing the circuit. Now what type of counter it is? 1 2 3 4 5. So once again, that is what? Mod 5 up counter. The correct answer is mod 5 up counter. Clear? That is how we are finding the output of the circuit. See, don't consider anything, right? Just observe the given circuit, right? Observe the whether if you have bubble, input is 0. If you don't have bubble, input is 1. Over. And just go with that input here. Anga enna value varudha and one if it is 0 or 1, inga enna varudhu paarenga. Idukku corresponding inputs enna irukanum அப்படிங்கறத choose பண்ணிக்கோங்க, right? That's all, right? And directly you can guess a few more things. Listen. Suppose நீங்க options வச்சு போய்க்கலாம். இப்போ suppose if some big circuit will be given, if you are unable to predict, then you can also go with the options. Anyway, இந்த ரெண்டு கேஸ்லயே உங்களுக்கு ஆன்சர் வந்துரும், right? Now if I ரெண்டு தான வரப்போகுது, see there, either it might be 0 or it might be 1. Only 2 cases are possible. It might be 0 or 1. Only 2 cases are possible, right? If it is 0 varunda, they will give you NAND gate கொடுத்திருக்காங்களா? NAND gate க்கு எப்ப 0 வரும்? When all inputs are going to be 1. Suppose if it is given as AND gate, then what will you do? For your AND gate output, அப்ப என்ன வரும் அப்படினா இங்க clear bar யூஸ் பண்ணிருக்க மாட்டாங்க, clear யூஸ் பண்ணிருப்பாங்க. If they are using AND gate, then they won't use NAND gate. They will use AND gate யூஸ் பண்ணிருந்தா இங்க clear bar யூஸ் பண்ணிருப்பாங்க, right? Sorry, clear bar யூஸ் பண்ணிருக்க மாட்டாங்க, clear யூஸ் பண்ணிருப்பாங்க. Clear means input is what? It must be 1, such that AND gate output is 1 when all its inputs are going to be 1. like that gates will be given to you. So directly you can identify just by looking at the combination 0 or 1 இதை வச்சு நீங்கள் கண்டுபிடிச்சிக்கலாம், right? Anyway, that method is not I don't want to waste your time, just to go ahead with this one, right? See, actually I have seen there was one more question, but I don't know where it is now. Yeah, this is here only. Let me take that one also, right? So let us remove this one. Okay, fine. Let us see, when circuit is given, once again I told you there are 4 circuit is given, right? So let me draw the circuit now. So let us draw the circuit. Yes, circuit 1. Let us consider the circuit 2, right? So let me consider the second one, and let us consider the third one also, right? Third one, and let us consider the fourth. They are given 4 flip-flops, right? 4 flip-flop means how many states are possible? 16 states are possible, right? So anyway, first let me complete the circuit. They said that is Q0 and Q1, Q2, Q3, right? So they went up with this given circuit, and they took 2 outputs, right? From Q1 they took a line, and then from the last here they took a line, and they just these 2 people, right, they will be joined with the AND gate. AND gate means immediately we need to think AND gate. அப்போ என்ன பின் யூஸ் பண்ணிருப்பாங்க? Definitely they will use what? Clear only. Now only I told you na, yes, that is what they are doing. They have to use clear pin. Then only AND gate will produce what? நீங்கள் லாஜிக்கை ஃபைன் பண்ண முடியும், right? So when your AND gate is clear pin, is there any bubble? No. If you don't have bubble, immediately input is going to be 1 1 only, right? See, there is no point of drawing rest of things, right? Okay, for your satisfaction, let me do that one also. Given it is negative triggering, that is negative triggering. Now tell me what type of counter it is, up counter or down counter? Hey, that is going to be 1 T flip-flop 1 T flip-flop 1 T flip-flop only 1 T flip-flop only. Now tell me whether it is up counter or down counter. First thing is, given it is negative triggering, but we are taking Q, right? See there, negative, where it is negative with the Q, negative with the Q, it is acting as a what? Up counter, opposite, right? So first of all it will act as a up counter, right? So we can simply say it will act as a up counter. First task is over. Now we need to find out the mod of the counter. In order to find out the mod, let us see, since given it is clear pin means what? You don't need to consider bubble, that is if you have bubble we have to pass 0, if you don't have bubble we have to pass 1, if there is no bubble we have to pass 1. See there, such that is going to be 1, and this is also going to be 1, right? So this pin also going to be 1. It means rest of pin values are 0. Getting me? It means rest of pin values are 0, right? Just to observe, they are taking outputs on the endendha flip flop வந்து எடுத்துப்பாங்கன்னா where we have 1 at the output states, right? 1 எங்கெங்கலாம் வருதோ, if you are considering அவங்க 1 ஓட ரைன்ஸ்லாம் வெளில எடுத்துருக்காங்கன்னா remaining all are 0. That's all. There are no more things to discuss, right? So this is going to be 1 and this is going to be 1, such that if I'll arrange, you'll have to start from here, right? So 1, next bit, that is going to be 0, again this is going to be 1, and then this is going to be 0, right? What type of number it is? What is this? See there, for equivalent 8 it is going to be 1000, for 9 it is going to be 1001, for 10 it is going to be what? 1010, correct? Exactly. When we are getting 10, when we are getting 10 we are getting back, that is we are getting back to clear. Why? Because we are designing up counter na, its initial state is 0000 and it is running up to 9th value in the sense 1001. See, in between 0 and 9 how many states are there? Totally you will have 10 states, including 0 0 0 0 to 9 you will have 10 states. Exactly when we are getting 1010 it is getting back, that is clear, right? So it will be cleared. So what type of counter it is? This is up counter and its value is what? Mod 10. So the correct answer is what? Mod 10 up counter. Your answer is mod 10 up counter. Guys, let me repeat once again. Circuit will be given to you, corresponding logic gate will be given to you. Either the output of the gate might be 1 or 0. Only 2 cases could be possible, right? Now if you have bubble then pass 0, if you don't have bubble then pass 1. If it is 1, corresponding inputs you can guess it, right? The type of, based on the type of the gate you can guess the inputs, right? For NAND gate output is going to be what? 0 when all inputs are 1. So NAND gate they will use when they will have what? Clear bar. They will use AND gate when they will have clear. Now see there, last case we took NAND gate because they took bubble here. This case we are taking AND gate. Why? Because there is no bubble. There is no bubble. So directly you can design the circuit. If there is no bubble, see their inputs are going to be 1. Now while designing the circuits, right, these inputs are being considered in the one in the line. இங்க எந்தெந்த லைன்ல வந்திருக்கோ அதோட correspondent flip flops ல மட்டும் தான் output 1 வந்திருக்கும். Remaining flip flop values are going to be 0. You can directly set that one. Getting me? So there is no point of discussing here, and you don't need to confuse yourself. You can directly post your answer. Remaining all flip-flop outputs are going to be 0, and then just arrange them and find out the corresponding clear state, post your answer. Don't do any bluff things. Starting la na varanjittu irukkenna edhum pannidadinga. It will spoil your time and you are unable to predict. There is no more logics. Identify the gate, identify the bubble and the corresponding inputs, post your answer. Over. Clear? I hope things are clear now. There are no things to discuss beyond this, right? Anyway, some people are making some different conclusions, right? Don't confuse with anything, right? So whichever the things that I had been told you, just keep it in your mind while solving the problem. If circuit will be given to you, just keep these things with you, right? If circuit alone will be given to you, just consider AND gate. Circuit alone will be given to you, just consider bubble without bubble. Bubble means 0, without bubble means 1. That's all. There are no more things to discuss, right? Now let us consider, let me rub these things. Okay, see there, if circuit will be given to you, see there, I am only discussing about clear pin. Right? So just to take, if circuit will be given to you, let us consider AND gate, right? Clear pin, and I am just talking about Q, right? So let us consider Q. They will take some logics, right? So let me consider NAND. Let us consider OR gate also. Let us consider NOR gate also. Right? இப்போ இந்த மாதிரி வந்து 4 சர்க்யூட் வந்து கொடுத்திருந்தாங்கன்னா, what I had been told you, it's very simple, right? Your target is just observe whether we are having clear or clear bar, right? Clear means it's correspondent, right? In order to activate the clear pin, I am in need of 1, right? Now 1 எனக்கு அவுட்புட்ல வரணும் அப்படினா what I have to consider, right? It's very simple, right? AND gate க்கு அப்ப see there, your gates, the gates that we are going to connect has to produce 1 as the output, right? Now this gate, right? So in this gate அப்ப நம்ம என்ன பண்ணோம் அப்படினா corresponding inputs are going to be common. It means AND gate output is going to be 1 when all inputs are going to be 1 1. Similarly, if you are considering NAND gate, right? NAND gate output is going to be 1 when all its inputs are going to be 0 0. Clear? So similarly, it means what we need to consider, the thing is, listen, AND gate கொடுத்திருக்காங்க அப்படினா input வந்து எங்க எடுத்துப்பாங்கன்னா Q ல இருந்து எடுத்துப்பாங்க. See, just if you observe here, we took the output from Q, and this output also we have been taken from Q. Why? Because I am in need of 1 1, right? Suppose if they are using NAND gate யூஸ் பண்ணிருந்தாங்கன்னா all inputs என்ன வரணும், 0 வரணும். அப்ப என்ன பண்ணிருப்பாங்கன்னா 1 க்கு ஆப்போசிட் பின்ல இருந்து வேல்யூ எடுத்துப்பாங்க. If you have 1, opposite pin is what, 0, such that they will consider Q bar with what? Clear pin. They will consider Q bar with what? Clear pin, right? Clear? Suppose if you are designing OR gate with once again clear. Once again, if I will talk about clear pin, see there, in order to இப்போ நீங்க OR gate வந்து activate பண்ண அப்படினா what we need to do, see there, output is going to be 1, right? So the thing is what, இப்போ OR gate யூஸ் பண்ணும்போது என்ன ஆகும் அப்படினா there will be a confusion, right? Confusion அப்படினா meaning என்ன, they will use, the thing is OR gate will produce 1 for all type of minimum 1 வந்தாலே output என்ன வந்துரும், 1 வந்துரும். அப்ப என்ன பண்ணுவாங்கன்னா they will take, see there, clear bar. They took clear bar. If you take clear bar, then what will happen, see there, output of the OR gate will become 0. That is a point where your clear pin will going to work. I am repeating once again, OR gate யூஸ் பண்ணும்போது என்ன பண்ணிருப்பாங்கன்னா we are using clear bar. Why we are using clear bar? Why? Because clear bar க்குனா clear bar க்கு நீங்க 0 பாஸ் பண்ணிக்கலாம், right? அப்ப நீங்க 0 பாஸ் பண்ண அப்படினா see there, when your OR gate will produce 0 when all its inputs are going to be 0, such that we are using what? Q bar, clear bar. That is the case where we are using OR gate. Getting me? Logic, you don't need to memorize. I'm just telling like this, you have to understand, right? So again, see there, if you are using NOR gate, once again, in NOR gate output is going to be 1 when all its inputs are going to be 0, otherwise it is going to be 0, right? Now see that, such that what will happen, here we are going to use Q bar as the inputs, and output is going to be what? Directly you can consider clear. Because what? Clear pin will going to consider, see, input la வந்து எல்லா கேட்மே வந்து 0 வரணும், I mean எல்லா possibilities 0 வரணும் இல்ல 1 வரணும். அந்த மாதிரி possibilities தான் questions will be framed. Getting me? So you can easily identify. You don't need to memorize these things, you can just observe these things, right? Okay, just understand, right? Don't memorize anything. Such that some I can also do the same combinations for clear bar. இப்போ நம்ம என்ன பார்த்தோம், கிளியருக்கு பண்ணோம் இல்லையா, இதே மாதிரி நீங்கள் கிளியர் பார் போட்டு NAND கேட்டுக்கு நம்ம யூஸ் பண்ணலாம். நான் சொன்னேன் இல்லையா, கிளியர் பார் வந்து NAND கேட்டுக்கு தான் யூஸ் பண்ண முடியும் அப்படின்னு சொல்லிட்டு. பிகாஸ் In clear bar output is what? 0. Clear bar output la 0 varanum, right? So what will happen? Clear bar ku neenga 0 pass panna appadina NAND gate, when all inputs are going to be 1, NAND gate output will be 0, such that we can use NAND gate for clear bar input, right? So that is how we are designing the circuits probably, right? I hope things are very clear now. So I don't want to confuse you further, right? So simply understand, consider the given circuit, right? Observe clear bar, bubble irundhathu appadina you will have to pass 0. If there is no bubble, you have to pass 1. That's all. There are no more to discuss. அதுக்கப்புற கரஸ்பாண்டா அவங்க என்ன கேட் கொடுத்துருக்காங்களோ அந்த கேட்டுக்கு இன்புட் என்னன்றது நீங்களே எடுத்துக்கோங்க. வேற எதுவும் நீங்கள் மெமரைஸ் பண்ண வேணாம், ரைட்? அவங்க கொடுத்துருக்க இன்புட் எடுத்துகிட்டு போயிட்டு அப்படியே ஃப்ளிப் ஃப்ளாப்பில் இன்சர்ட் பண்ணுங்க. இன்சர்ட் பண்ணிட்டு ரிமைனிங் இருக்க ஃப்ளிப் ஃப்ளாப்ஸ்க்கு 0 போட்டுட்டு என்ன கவுண்ட்னு பார்த்துருங்க. தேர் ஆர் நோ மோர் திங்ஸ். ஓகே, சிம்பிள். நம்ம எப்படி சால்வ் பண்ணுமோ இதே மாதிரி தான் இருக்கும் கொஷின்ஸ். ரொம்ப காம்ப்ளிகேட்டடாக we cannot design complicated questions here, right? Okay, I hope things are very clear. This is all about what I can say non-binary counters, right? So now with this let's wind up but let's wind up the synchronous asynchronous counters, right? So in asynchronous there are 3 types of counters. First we saw ripple counters. In under ripple there are 2 types. One is up counter, another one is down counter, right? Apart from up counter and down counter, we will also be able to, that is we can also design what I can say non-binary counters. So that is the procedure that we saw. With the help of this procedure we can design what? Non-binary counter. Now we are going to design synchronous counters, right? So our next target is we have to design synchronous counter. So let me design the synchronous counters first. So keep that in. We are going to design what? Synchronous counters, right? So let us design the synchronous counters circuits, right? So synchronous counters. Let us design synchronous counters. Yeah. Now how will you design the synchronous counter? It's quite interesting, and of course it is very simple actually, right? Synchronous counter la first thing we are going to design, right? So that is called ring counter. So the first thing is we are going to design is simply called a ring counter. Guys, I told you synchronous counter in the sense all flip-flop will going to be synchronized at a time, right? Now you might be wonder, sir, why we are designing a synchronous counter from asynchronous counter? What is the purpose? The thing is, in asynchronous counter any type of sequence we can bring, right? And I said a non-binary counter, we will see, right? Any type of sequence, random sequence I will teach you at last, right? So any type of sequence could be possible, and what we saw, we have seen many advantages, right? In the non-binary counter, right? All countings we have done, but the issue with that one is all flip-flops are not synchronized at a time. It means your circuit will produce some delay, right? There will be some delay, that is called propagation delay. That is called propagation delay. There will be a drawback, right, in our asynchronous circuit, that is simply called propagation delay, right? If you observe this propagation delay, how to overcome this one, right? So while that is, if you are calculating, that is the required clock, right? The required clock is you need to catch, right? You need to catch the flip-flop, right? So first of all we need to catch the flip-flop, that is propagation delay offered by the flip-flop. Let me consider propagation delay, right? What I can suggest here, let me consider propagation delay of the flip-flop we need to consider, and then we have to consider the delay offered by the gates. Like you may consider some gates here, logic gates, right? They will give you propagation delay of the gates also, right? If we have a single flip-flop, then we can treat like this, propagation delay plus what I can say t flip-flop, right? That is a gate flip-flop. Suppose if we have 4 flip-flop, then you have to multiply it by n. Let me consider n. 4 flip-flop means it is 4. Listen guys, this is how we are calculating the clock, right? Your value of the clock should be what? It has to be less than or equal to this, that is minimum, at least its minimum value should be equal to what? N times of TPD plus gate. Very simple. Total propagation delay வந்து calculate பண்ணிட்டு we are triggering the circuit, right? Total propagation delay என்ன வரும்? 1 flip-flop ல எவ்வளோ delay வருது, total number of flip-flop எவ்வளோ plus clocks, right? So from this we can find out the maximum frequency. We can find out the maximum frequency. The maximum frequency is at what? The maximum frequency is 1 upon t clock. Simply we can overcome this. That is, we can calculate the maximum frequency. Anyway, the problem is here we have propagation delay. We have propagation delay. In order to overcome this propagation delay, right, we are moving on to the next type of counters, that is called synchronous counters, right? So let us remove these things now. Okay, first type of counter we are going to design is called a ring counter, right? So we are going to design ring counter, right? So that is very simple guys. Let me design, right? In order to design the ring counter, anyway here we are not going to provide any togglings, right? Such that, right, we can use directly, let me use a D flip-flop here. We are going to use D flip-flop because I told you we are going to design ring counter. Ring means what do I mean? Let me show you. Just observe the circuit itself, you will come to know why it is called ring counter. Why it is called ring counter, right? That is the type of the circuit that we are providing here. Clear? And the next thing is, of course, this is going to be Q2, this is going to be Q1, this is going to be Q0, right? So let me call it as T2, this is going to be T1, this is going to be T0. Now see there, we are designing what? Synchronous counter. Synchronous counter in the sense all counter will be synchronized together such that either you can use see there, you can use level triggering, you can also use edge triggering. It does not matter which type of triggering that we are going to use here, right? You can use all type of triggering here, right? Let us see how to design the circuit. Sorry guys, I took D flip-flop I said, but I wrote T flip-flop, right? Fine. First of all, what do you mean by D flip-flop? Data transmission. Whichever the data that we are giving in the input side, it will be transmitted to the output, right? Such that its equivalent circuit can be drawn like this, right? So we are considering 3 box here, right? So 1, 2, 3, such that output of this one is going to be again reinserted, right, as the input of the first flip-flop, right? So let us see, and with this we are also providing clock here. Now the thing is, initially let us assume, right? So initially we are having the output state as 1 0 0. We have to register initial state, you need to register, right? So let us assume your initial state is 1 0 0. That is the initial state. Now when we are giving one clock, right? So one time neenga synchronize panninga appadina what will happen? They will start, this 0 will be shifted here. Guys listen carefully, observe first of all how this flip-flop will work. The thing is, data transmission flip-flop, whichever the input that we are having here, inga enna input irukka adu appadiye output ku shift agum. See there, inga 0 irukka, this 0 actually is waiting here. When we are giving the first clock, enna agum, data transmission flip-flop input la enna irukka adu appadiye output ku transmit pannum. So this 0 will come here. Whereas this one, see there, all flip-flop will be synchronized at the same time. It means idukku munadi inga 1 irundha, that 1 will be transmitted to this point, this 0 will be transmitted to this point. So while giving the first clock, your next state is going to be 0 1 0. We are going to get 0 1 0. That is when I am applying the first clock. Now let us assume in the second clock what will happen. See there, your new states are 0 1 0. Now when we are applying one more clock, see there, this 0 will come here once again. Now while giving this second clock, see that this 0 will be shifted, at the same time this 0 will be shifted, this 1 will be shifted here, synchronized, right? So this data transmission will happen at the same time, right? Ore time la nadakum ellame, right? So they will be synchronized such that your next state will become 0 0 1. Now let us discuss about third clock such that this 1 will come here, 1 will come here. Again when we are giving next clock pulse, see that this 1 will be shifted here, of course, this 0 will be shifted here, of course, that 0 will be shifted here, of course, coming back, right? Now what is the conclusion here? The next thing is, once again, if you are applying next clock pulse, it is again and again being repeated, it will be again and again being repeated, right? So how many states are will be, that is how many states will be repeated here? Totally 3 states. Did you observe? Right? So we are repeating here. How many states will be repeated here? 1 2 3, right? So how many flip-flops are there? 3 flip-flops. How many states it is producing here? 3 states. So what is the conclusion? Number of flip-flop and number of states are equal. Number of flip-flop and number of states are equal. Number of states are equal. First thing, right? Number of flip-flop and number of states are equal, right? Now whereas let us assume this is the output port. This is the output port. Now what we have understood here, in this output port totally we are receiving 3 states, right? But what is the duty cycle? If you observe in the output side, right? So we had been applied 3 clocks, right? So we had been applied 3 clocks. Let us assume initially I have 0, first clock, second clock, third clock. It is going like this, right? First clock, second clock, third clock, such that what will happen in the output side, right? In the output side, if I'll consider three flip-flops, right? Output frequency, we know, okay, directly let me write, we know the output state V0 is, that is F0 is going to be input frequency divided by number of flip-flops that we are considering, or the number of states that we are receiving in the output, right? So directly let me place the answer, right? So totally this is going to be what? Fn by 3, that is going to be the output frequency of the flip-flop. Clear? Anyway, this is called what? Ring counter. But in this ring counter there is a drawback. The drawback is initially we need to register the values, right? This is called what? Non self-started ring counter, not self-started ring counter. It is not self-starting ring counter. இதுவாகவே ஸ்டார்ட் ஆகாது, நீங்கள் தான் ஸ்டார்ட் பண்ணி விடணும். You'll have to apply some values and then you'll have to start the circuit, then it will count the state, right? If see, suppose if you have 0 0 0, then what will happen? If you have 0 0 0, as long as you are applying the clock pulse, there is no changes in the states. 0 0 0, again 0 0 0, again 0 0 0. The state is again and again being repeated. You cannot count anything here. So the conclusion is what? You'll have to register some value. Initial state, initial starting will be provided by, that is manually we have to provide, right? So this is not self-starting, right? So let us design. This is ring counter only, but that is not self-starting. Let us design the self-starting ring counter, right? So our next task is we have to design the self-starting synchronizing ring counter. We are designing synchronous counters only. This is self-starting, sorry, this is ring counter, but it is not self-starting, right? So let us take self-starting ring counter, right? So let us consider self-starting ring counter. Okay, so let me remove these things. So let us take self-starting ring counter. Okay, self-starting ring counter. It means what we are going to do. For your best understanding, let me consider, okay, let us consider 3 flip-flop. I hope this is enough, right? I will design. Okay, I just go ahead with 3 flip-flop only, right? Because I can design, no issues. Okay, let me join these two people together, and I'm going to consider them with a NOR gate, that is NOR gate. This is going to be the input, and we are going to collect the output here. We are going to collect the output here. This is self-starting ring counter. Self-starting ring counter. This is simply called self-starting ring counter. We are simply called this one as self-starting ring counter. Now let us design this self-starting ring counter. Once again, we are designing what? Synchronous counter. We are designing synchronous counter. While designing the synchronous counter, our target is what? Target is we have to achieve, or we have to synchronize all the flip-flop at the same time, right? Now what it will do, the thing is, for an example, initially all the values are 0, right? Let me consider Q2, Q1, Q0. We have not registered any values. All the values are 0 0 0. Now first of all, what is the logic of NOR gate? For 0 0, output is going to be 1. For rest of all possible inputs, NOR gate output is 0. Do you all agree with me? Whenever your all inputs are going to be 0, corresponding output is only going to be 1 for NOR gate. For rest of all possible inputs, output of the NOR gate is going to be 0 only, right? We know this one, right? So let us proceed with this. Now see there, let us start. It's equivalent circuit, right? So let me draw the equivalent circuit also if you want, right? So let me draw the equivalent circuit. So we are considering 3 states here, of course. Now in these 3 states, what we are going to do, this is the third state, of course. I don't want this one, right? So we are just taking, okay, let me do one thing here itself. Let me take the output and let me join it with the NOR gate, right? So let us join it with the NOR gate such that once again it will be given back. It will be given back, right? So let us see. Initially all the values are 0. All the values are 0. Now what will happen when we are giving the first clock? While giving the first clock, see there, this 0 0 will come here, right? Anyway, clock apply panla. Just wait. Before applying clock pulse, 0 0 will enter here. This is gate. This gate will produce what? NOR gate. For 0 0, output will become 1, such that 1 is waiting here. Now when we are giving the first clock, automatically what will happen? Initial state is 0 0 0, right? That is with the 0 clock. While applying the first clock, automatically it will become what? See there, this is going to be Q2, Q1, Q0. This is Q0, this is Q1. Okay, let me write in the same order for your understanding. Let me do one thing. This is Q2, this is going to be Q1, this is going to be Q0. Just for your understanding, I am writing it in the same order, right? Okay, let us start. See that initially we are having 0 0. While applying first clock pulse, automatically 1 will be injected into this black. Automatically here it will become 1. Rest of people are going to be 0 0. Now while giving the second clock pulse, let us see what will happen. See there, now the new states are 1 0 0. Now such that 1 0 will give you what? If I'll apply, see there, here it is 1, here it is 0. While applying 1 0, the NOR gate output is what? We all know NOR gate output is going to be 0. At least you will find minimum 1, automatically output will be 0, right? Such that what will happen? 0 once again. While applying the second clock pulse, 0 will be injected such that it will become 0. Again this 1 will be shifted to this point. This will be shifted to this point. This 0 will come here. Since we are designing what? Guys, listen, one thing you have to understand. This is D flip-flop. D flip-flop in the sense data will be simply transmitted. So we no need to worry about these things. Sir, which type of gate that we are passing? We no need to worry about, draw the truth table of this flip-flop. Don't do blob things. This is simple, beautiful D flip-flop. Whichever the data that you are transmitting, that will go. right? We don't need to think whether it will be complemented or it will become 0 or 1, no need. Whichever the data that we are passing, transmitted, that's enough, right? So while applying the second clock pulse, this is the new data, such that actually, let me explain here also, this is become 0, this is become 1, that will be 0. Now let us apply third clock pulse. See there, before applying the third clock pulse, 0 1 will once again come here. 0 1 means output once again 0 only. Now while applying the third clock pulse, 0 will be injected or transmitted, such that this 0 will come here, this 1 will go here. Now when we are applying the fourth clock pulse, let us see. Now while applying the fourth clock pulse, let us see what will happen. Now when I am applying the fourth clock pulse, the thing is, see there, now what will happen here? We have 0 0 1 na? Right, we have 0 0 1 0 0 0 0, what will happen? See there, we have 0 here, right? 0 0 once again will enter here. 0 0 will produce what? 0 0 will produce 1, because we are discussing about NOR gate, right? So once again while applying, it will be injected, it will inject what? 1 will be injected here. Again what will happen? This 0 will be shifted here. Again what will happen? That 0 will be shifted here. Next what will happen? See there, did you observe? We are getting the same state as it is. Anyway, this is initially we have not no எதுமே இல்ல அப்படிங்கறத நான் 0 0 ன்னு கன்சிடர் பண்ணிக்கேன். Now how many states are there? State 1, state 2, state 3. Same state will be going to be repeated again you will get 100 0 1 0 0 0 1, such that how many flip-flops are there? 3 flip-flops are there, 3 states. They will repeat 3 states. 3 states will be produced. They will produce 3 states. Clear? And output frequency is what? Input frequency divided by number of states that we are considering. It's over, that's all. Directly we can post your answer output, and we can also consider your number of states at all. Clear? I hope things are very clear now, right? Okay, fine. This is all about what? Ring counter. But this is called what? Self-starting ring counter. I no need to do anything. Initially, though all values are 0, NOR gate will do this work simply. Your work is what? You will have to synchronize the circuit, you will have to apply the clock pulse. It will do its action automatically, right? It will bring 3 states, and those 3 states will be again and again repeated. Clear? Like our clocks. What will happen? After reaching the 12 o'clock, again your counter will start counting 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12. Again it has to count the same state. This is called what? Clock type of counter only. So we can design what? There I made of what? 12 counter, mod 12 counter. Because such that what will happen? Mod 12 means it will count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12. That is mod 12 counter will be, we are using it in the clock, right? That's all. Right? In case of railway time, we are using what? Mod 24 clock. Okay, let us see. This is all about what? This is ring counter, right? So let us design complement of ring counter, that is called what? Johnson counter, right? So let us design the complement of the ring counter. Next we are going to design complement of ring counter. Let me design complement of ring counter. That's easy. Let us consider only 3 flip-flops once again. Let us consider only 3 flip-flops. Consider only 3 flip-flops. That is enough. Now what we are going to do in this 3 flip-flop, once again, see there we are going to use D flip-flop, that is D only, D0, D1, D2. Let me join them together. Right? And this one will become, see there, let me take this one. Let me join this one with this one. Just observe the difference between ring counter and this one, right? And let us see. And they will be what? Synchronized together, because since we are designing what? Synchronous counter only. Since we are designing synchronous counter, right? So it means all flip-flop will going to be synchronized together, right? This is Q2, Q1, this is going to be Q0. Let us draw the equivalent circuit of this one. Actually we took 3 states, right? 1, 2, 3 states we took, right? Last state, see there, guys listen, last state complement editing, you are getting Q0 bar, right? That is going to be the input of the first flip-flop. It means complement in the sense, just to take the last state output outside and connect it with the inverter. Am I correct now? Because complement of the last state is going to be the input of the first one. This is Johnson counter. Clear? Of course, right? So let us see how to design this one. So initially let us assume all these values are 0 0 0, right? All these values are 0 0 0. Initial state is 0 0 0 only. Initial state is 0 0 0. This is the point where we are going to apply clock pulse, right? So let's start our journey, right? 0 clock with all initial states are 0 0. Let me consider Q2, Q1, Q0. Clock is 0 now. When we are applying the first clock, listen, it is 0 na, appo inga enna irukum 1. This 1 will come here, it is waiting. this 1 is waiting now, such that when we are applying the first clock, immediately this 1 will be transmitted to this point, such that see there, this 0 na inga 1 inga vandirukku, right? So Q2 will become 1, rest of guys are going to be 0. When we are applying the second clock pulse, then what will happen? See there, actually what will happen, carefully observe. While applying the first clock pulse, this 1 will come such that this place will become 1, this place will be 0, again it will be 0 only. If it is 0, again it will become 0, 1 only, na? If it is 0 means opposite is what? Complement. Such that once again we are getting one more 1. Now while applying the second clock pulse, observe here, this 0 will be shifted here, this 1 will be shifted here, we have 1, this 1 will be shifted here, such that here we have 1, and this 1 will be shifted here, this 0 will be shifted here. Let us observe the third state. Anyway, the new states are, this is 1, this is also going to be 1, here still we have 0 only, 0. Complement of 0 will become 1 once again. Now again if you apply the next clock pulse, this 1 will come here, this 1 will come here, this 1 will come here. If it is become 1, automatically it will become 0, so this 0 will come here. Now let us apply. While applying fourth clock pulse, 0 will enter inside the circuit, this 1 will go here, this 1 will go there. While applying fifth clock pulse, let us see. Again now new states are 0, 1, 1. Again still we have 1 only, na? This 0 will come here once again, this 0 will enter here, this 0 will be transmitted here, this 1 will go outside. Let us apply sixth clock pulse. Again what will happen, we are getting what, still anyway 0, 0, 1, we have 0, 0, 1. Again if we have 1, still it is 0, again this 0 will come here, such that 0, again this 0 will go here, this 0 will go here, such that all will become 0. Again what will happen, you have to get back to the circuit, you'll have to get back to the circuit. See there, if you observe these things carefully, what happened here, this is the state number 1, state number 2, state number 3, state number 4, right? Again state number 5 is repeated, state number 6 is repeated. Again when we are getting back, that is seventh state varumbodhu enna once again we are getting back, that is initial state. Clear? So what will happen, how many flip-flops are there? 3 flip-flop. How many states are there? 6 states. 1, 2, 3, 4, 5, 6. Getting me? Same state will be repeated, na? So the number of states is equal to, write on the statement, number of states is equal to twice of, right? Twice of number of flip-flop. Do you all agree with me? How many flip-flops are there? 3 flip-flops. How many states are there? 6. 2 into 3 will give you 6. So number of flip-flop into 2. Number of flip-flop is 3. 3 into 2 will be 6, na? So number of states should be equal to 2 twice of number of flip-flop, right? So in general that will be 2 into n. N denotes the number of flip-flop. Clear? That's all, right? So then what automatically what will happen? Output frequency will going to be input frequency divided by number of states only, na? How many states are there? Twice of n. So the output frequency is input frequency divided by twice of n in case of, this is what? Johnson counter. This is called Johnson counter. I hope things are very clear to you all, right? So that is how we are bringing the output in case of Johnson ring counter, right? So this is how we are designing synchronous counter circuits. Once again, I found a question in this part. I don't know where is it. No, it is not available. Okay, only general counters are there, we will see later. I don't know where I have seen that question bank, I lost. Fine. So this is how we are designing synchronous counter, right? So anyway, till now we saw how to design the general circuits, right? And we learn in asynchronous counter also we learn how to design the circuit, right? Now we are in synchronous counter, and we learn in synchronous counter also. Now we know we saw some standard circuits. Now apart from this, we have to generally design the circuits. General circuits in the sense, we can take randomly some sequence will be given to you, right? And next state we have to what I can say, some random sequence will be given. With the help of the random sequence we have to design the circuit, right? That's all, right? That procedures, that things at all we will see tomorrow, right? Of course the counter is over, right? Only small topic is pending, right? Immediately with that we will solve some problems, right? And then we will start shift register will be there. With that your sequential circuit is going to be over, right? There are no more things to discuss. And apart from that, there are one more topic is pending now in digital, that is we need to discuss about converters, right? Very important topic, and it is quite interesting actually, right? That's all. I hope things are very clear to you all, right? If you have any doubts, please rewatch the video once again, right? There is no issues, right? You'll have to observe all those things, and especially keep your concentration in the finding, that is in finding the mod type of counter, whether it is mod 5,
mod 6, mod 7, right? Very simple logic. Anyway, circuit will be given to you. Don't worry about the type of the gate that we are considering. Forget anything, right? Forget all things. Just consider the output input. Clear? Clear bara. Preset preset bara. Corresponding input where pinned enorum. It's over. Don't think anything beyond that. You will get the answer. It will be tested for 2 more questions, right? So just rewatch the video once again. Should try to collect the data properly. Clear? So with this, let's wind up the class. If you have any other doubts, you can ask in the group, right? Thank you all.